Hello, everyone. I hope you're doing well. You're doing fine. Here we are. We meet again another Friday, 12 noon, for another chit chat about an interesting topic and something that um, is hot topics of this time. And actually, I am so hyped up about today's topic. Reza, how are you doing?
I'm good, wonderful. Thank you for having me
It's
on your program. Yeah.
It's my pleasure. It's AI is in everything today. Artificial intelligence. Ever since that, what was it? The movie called I Robot. I forgot the name of the movie. Um, the one was Will Smith, if I'm not mistaken, and everyone is waiting for the time where the world will be run by machines. So Reza, how are you doing? How's everything? And you're coming to us from Norway.
Yes, I'm in Bergen in Norway, the western part of the Norway, and yeah, so far so good. Everything's nice. Yeah.
This is awesome. I was sharing with you earlier that I had a childhood dream that I will move to Sweden. I will not share the reasons why. It's not very scientific, but I was well. Here you go. I'm gonna share it. I used to love a pop band from Sweden called Ace of Base. I
Okay.
was
Yeah, I
I
know
was
that.
a big
Yeah.
fan, and I'm like, someday I'm just gonna go there.
Yeah. Sometime you can come over and visit. Yeah. And Sweden is not far from here.
I would love to, and actually someday, I mean, definitely that should happen. So, waiting that people are joining us. I can see the attendance is going up. If you guys want to say hi to Professor Arghandeh, go ahead and say so. I see a lot of people. That's awesome. So let's go ahead and get started a little bit and talk about the collaborative intelligent infrastructure lab that you lead at in Norway. But first, I usually present people myself, and I have your LinkedIn ready next to me to talk about where you've been and everything. But you have a awesome chart, so
Thank
so I think we're gonna go with the chart, and I'm gonna let you introduce yourself because you've been a little bit all over. So go ahead, talk to us a little bit, Reza, about you.
Thank you. Yeah, that's my infographics. Basically, I'm a Reza Arghandeh, and I'm from Iran. That's where I got my bachelor in electrical engineering from Khaja Nasser Tusi University. It's a technical university in Iran. And that time I was focused on telecommunication engineering, but I was so fascinated with energy since we have the huge resource of energy, oil and gas back home in Iran. And that's the reason I moved into the field of energy systems, energy engineering. So in 2008, I got my master in mechanical engineering, but focused on energy systems in with University of Manchester and also my home institute, KNTU in Iran and UK. And that was the time I decided to go for PhD. I got so fascinated by university and research, so I moved to the US. I joined Virginia Tech to get my PhD in electrical engineering in power system. And at the same time, I also got a master in OR, operation research, which was more focused on optimization for networks. And basically, my focus and my interest was more into the creating monitoring system and data acquisition for electric grid, and basically think about how can we deal with this data, the data that comes from a smart meter, from SCADA systems, from the power quality meters, and so on. And after graduation in 2013 from Virginia Tech, I joined UC Berkeley, and I spent 2.5 years in Berkeley as a postdoc scholar, and I worked mostly on the machine learning algorithms and data analytics, especially for time series and spatial and temporal data for the electric grid. 2015, I joined as assistant professor to Florida State University, where I founded and started a collaborative intelligent infrastructure lab. And I devoted most of my time and research on using AI for smart grid with connection to other networks or or in other words, smart city. And in 2018, I moved to Norway, to Bergen, and here I'm a full professor in Western Norway University of Applied Science, and keep going. Yeah, I'm
That's
also
awesome. I mean,
start.
this is a super interesting career so far. You've been in Europe, you came to Virginia, to California, to Florida, back to Norway,
Yeah,
and such a short span. I mean, in the last what, 15 years.
yeah.
So this reminds me a bit of myself.
These days we are the citizen of the world, so it's. I think it's good to have a taste of different places and get connected to people all around the world. Yeah.
What you said, I believe, I fundamentally believe in it because if we like my viewpoint of how I perceive things when I lived in France, it became different from what I had was in Lebanon. When I went to Indiana, when I went to lived in Virginia, and now South Carolina, it's so different. Even within the U.S.,
Yeah.
people think that it's the same. Well, it's so different when you move from one state to the other, and it is a little bit fascinating. Reza, there is a ton of people saying hi to you.
Hi,
I'd like to ask
everybody.
I'd like to ask something from folks on the chat. If you can say hi, where you're from, because this is fascinating. The fact last week we did that, and we really almost touched all over the world. So I know Kevin is from the University of South Carolina, so he's from here. We have a hi from Rwanda, from Alana.
Nice. Hi, Rwanda. Yeah.
We have hi from Simeon Liev. We have from Alisar, from Ali. So it will be interesting if people listening to us now just throw where you are, and at any point in time, just ask a question. This is really meant as a friendly chat, and we get to know something, and we all get by the end of this session a little bit smarter. So Riza, let's talk. Let's start talking a little bit about today's what you're going to cover is really is artificial intelligence for smart cities, and the goal. So the highs are coming in from Raleigh, North Carolina, from Beirut, from the American University of Beirut. Hi to Naveed. So this is please keep bringing it up then. So you're gonna talk then about co-mobility and co-resilience. What is co-mobility? Like just as a definition before we delve into it, what does co-mobility means?
Well, when we decide to select a name for the lab, basically, I really fascinated with a collaborative because I'm all in for collaboration. And I think the infrastructures is really just a society built from steel, from wire, from copper, aluminum, and from fiberglass, So from polymers, but that this the infrastructure we build because we human as a social thing, social entity build a system. That system by nature is social, is collaborative, is communicative. So I really like to we emphasize on these aspects of interdependency and interconnectivity between different infrastructure within a city or even in the national level. So collaborative or the co means that they are collaborative, connected, and they work together. When I say they, I mean different layers of the infrastructure, including electricity network, transportation network, telecommunication networks, a social network, and so on. So co-mobility means that the mobility in a context of a connected infrastructure networks, or co-resilience, the same. If we want to make a network, an infrastructure resilience, we need to consider the interdependency and interconnectivity of that network with other type of the network. So the comes from collaborative and connectivity.
This is awesome. I'm looking forward for this. I believe that the more we get these metrics in place, the more we can actually fight corruption at systematic level. And although what we're doing it for the science and to improve things, but the more things are data backed and the more things are connected, and this would be great against the fight against corruption whenever it's possible as well. So you are at the Western Norway University of Applied Sciences.
Yes.
You are in Bergen, or which one of the five campuses?
I'm in the Bergen. Bergen is the main campus of the university. So, and we have four more campuses in different parts in the western part of the Norway. Yeah, and Bergen itself is a very beautiful city and kind of a touristic hub for Norway, and people come here and they go to visit the fjords here. So very beautiful nature.
This is awesome. So I'm gonna take you up on the visit one day.
Absolutely. And yeah, and here I put some more information about the university and who we are. It's a young but very dynamic organization, and yeah, and basically,
If you have an exchange program, it would be interesting to like ask perhaps some of the undergraduate students in my research team and like in your team, perhaps this is something we can work on, because that would be interesting. And then I would have the excuse to go visit the student in your university.
Yeah, we have very active mobility and visit program for students, undergraduate and graduate, and there are different schemes for students to come and visit us. Yeah.
All right, talk to us about your lab. So this is the result of 12 years at different universities.
Yeah, that's kind of, yeah, exactly. So yeah, because as I started to learn more and more about, I started with with the telecommunication network actually, and then move into the electricity networks. But the network theory and the system was always in my mind when I was looking into the infrastructure. And later on, I found out how mobility, transportation, environments, the communication, all these aspects are very tangled and interrelated. So we believe in CI2 Lab, the infrastructure, people, and environments are all connected and tangled as a one story together. When it comes to design, operation, and planning for any type of infrastructure, we need to first look into that, who's going to use this infrastructure. We need to pay attention to the citizens, to the people, and the way they are using this kind of utility networks in terms of energy, mobility, water, gas, and whatever. Also, we need to take care of the environments, the place, the ambience we want to build this infrastructure and use it. So really this collaborative sense is there. And we try to model it with data-driven approach, with machine learning, with AI. And the reason we are interested in AI, because the infrastructure networks, they are huge, they are so complex. It's very hard to algorithmically basically solve this problem, model them, and analyze them. So we need to use this kind of better tools, and we found those tools in AI and in machine learning.
You know what? One of the questions is, and I see it in here, is people. How do you even like, how do you integrate something that is not predictable, or are we predictable, like to the point where we can be modeled in terms of like I see infrastructure, I see environment and people. As a city, it's a living organism. So how do you put people into that equation?
Very good question. I would say people are predictable to some extent, and especially when we put all these people together as a society, as a community, then it's easier to predict their reaction. For example, when we consume electricity, or electricity consumption pattern as a household level, will have a lot of intermittency or variation. But if we start to look at our smart meter data for a year, 2 year, 5 year, we can extract different patterns in this smart meter data, and in other words, we can predict our behavior or the way we consume energy. So people are predictable when it comes to the electricity consumption. And when I look at the whole city or a community or a neighborhood, and we put all these people together, this collective electricity consumption, even it's more predictable because
Okay.
it has less noise or less variety, Inter-
How did these patterns change with COVID? Like because people are switching to work from home.
yeah.
So how did these like did you guys do some research on like these pattern change? Did you look into that?
We are working on the electricity consumption patterns for a couple of years, and we didn't do that specifically for COVID in a specific area, but we look at the general change and the trends and what the utility basically doing, electric companies doing with this kind of the change in the work from home habit and so on. So what happened? Yes, the amount of electricity consumption in the area which are mostly residential these days during the work day and weekends get closer because more people stay at home and they work from home, And the area that for the office space, the commercial area, the financial districts, so because they have less people in offices, so they have this kind of the demand drop. But the important aspect is that how these patterns are important for electric companies, how they be affected by this change in electricity consumption pattern. So the so
Yeah.
and the,
This is,
yeah, that's the main question, and the answer is kind of they need to be prepared to provide electricity for people wherever it's needed. So they need to have some kind of prediction about in next hour, next day, next week, which area would need more electricity or less.
so this slide does a good job, like summarizing what we've been talking about. So basically, what you're saying is that your research core is you have the energy, you have the transportation, you have the population, you have the information systems. All of these are outputting data and flocking tons of data. And at one point, you collect all of these data, you process it. Of course, I cannot imagine the semantics, how tough they are to actually, make sure that data, like they're not speaking different languages. And then you're using certain models, and the goal is to have support systems for the infrastructure networks across a city of what's happening in a city.
Yep.
All right, so you're gonna take us into two example projects now, one on
Yeah.
co-mobility and one on co-resilience. A couple of things is, first of all, if you have any questions, please post it to us. And Reza, as you can see, we've covered all continents. You have from all the way France to the United States to Indonesia to Iran to Lebanon. So
That's,
so we have a very wild and awesome spectrum of people that we can reach.
that's the
All right.
beauty of connectivity, and it's always good to make the connectivity collaborative. So that's where we can do big things together.
All right. So what are we going to talk about this? What is it that we're um, what is the co-mobility combined
Yeah.
traffic and electricity forecasting section?
So let me start with a short story. Just imagine yourself this morning when you come to the office. So when you wake up, the first thing you do, I'm sure you reach out to your phone and check your cell phone for your message, email, or thing. I'm not sure you, but I'm talking about myself. So
Oh, we're all in the same boat. We're all in the same boat. I
yeah,
actually force myself to have a detox period every year from like almost December 1 to like January 15, where I shut down all my electronics.
that's
So
awesome.
after that, I'm like, just like the social dilemma.
Yeah, exactly. So we start our day with using some electricity, and then we go take shower, go to the bathroom, start to use some water, and another some more energy, and then come make the breakfast, toast or bread, put some butter, and then make a coffee, use electricity, right? And maybe after 20-30 minutes we get out, take our car or use the metro, bicycle, bus, whatever, go to the works. It takes us 30 minutes, go from home, come to the university, to the office, start to work. And the first thing we do at work, turn on the lights, turn on the computer, start to check the emails, and start to work. So me as a person using electricity in two different locations, in two different times. Just imagine, not me, the whole people in the city having this kind of patterns. So if the electricity company have some kind of indication where I am and how I'm going from point A to point B, it can imagine how the electricity need to be provided for me and for all other citizens to be able to do our life, to do our works and to be convenient, right?
Yep.
So the electricity consumption pattern is connected with the mobility patterns. And what makes them connected are citizens, are the people and the way they move within the city in different neighborhoods, different locations. That's the story of traffic and electricity and how they are connected. We try to make a model for this, a data-driven model to extract these kind of patterns in electricity and traffic and put them together to come with the same story. Here I have an example of the city of Tallahassee in Florida. That's the projects we done while I was in FSU. And for example, we pick a neighborhood in the southeast of the city. So we have around maybe 200 houses in that neighborhood. And we have the smart meter data for these houses. Also, we have the measurement for the traffic that is passing from the nearby passing highway, and we know the number of the cars. We can measure it. So at the right hand side, I just pick randomly one of these houses on a random day, and then for the same day, I look at the traffic pattern in the northbound and southbound of the highway, the number of cars. The blue line you see here is the electricity consumption for one houses. The orange line is the traffic in the northbound when the people go to the downtown, to the center of the Tallahassee to go to the work, to university, offices, and so on. And the dash green line is the traffic in the southbound. When the afternoon, these people come back, go to the home or wherever they are. Even visually, we can see that some similarity between the morning peak in that random house and the morning peak at the nearby highway. And afternoon, we have this kind of coincidence between the traffic peak and the electricity consumption peak at the same house. So we try to look at all these time series, all this data, and extract this pattern to come to some conclusion, some model. And with that model, by looking into the electricity consumption, I can give you some hints about the traffic. Or by looking at the traffic, I can come up with some idea about the electricity consumption in that neighborhood, that city, the whole state, and so on. So that's what we call this CoMobility, looking into the mobility in the context of energy consumption and how we can model.
This is awesome. I was asked to zoom on the figure as you were talking, and I can zoom more than this, but basically, Ali, all the charts will be uploaded to the, and I will show it at the end of today's session, and you can have access to them again and talk.
Yes.
To actually, like the link also to add Reza as well on LinkedIn, and you can continue the discussion with him if needed.
Yeah, and all these works are published, so the papers are available. So maybe they can also look at the papers for that.
Yep, that's awesome.
So the way we do this mathematically, basically, we look at the weather data, because the weather is very important. If it's sunny and nice weather there, maybe people would like to just walk to the work, or you take the bicycle, or if it's a rainy day, definitely they want to take the cars or use the bus and so on. So the mobility pattern is a function of the weather condition. The same way, the electricity consumption is highly correlated and dependent on the weather condition. because of the air conditioning systems and the way basically we use electricity is related to the ambient temperature, humidity, and so on. So one part of the story is weather, the other part is the traffic on highways, on roadways, and the electricity consumption in different neighborhoods. That's what we look into. So but the question is that, as you mentioned, we have tons of data. We have an ocean of the data. How we put them together? How we can make something meaningful out of using this data? That's where we use the causality analysis. Causality is a branch of machine learning which look into the cause and effect relationship between different variables or data set. And we try to come up with such a graphical models that you see here. And basically we model the data sets, the variable as a different nodes, and we try to connect them by some directional edge to see what is the cause and what is the effect, you know. And when we can find the main causes, the main reasons, we don't need to look at the whole effects, you know. We just work with the major components or the major variables. And that way we reduce the size of our problem. We compress the dimension of this problem and we focus just on main figures. So for example, in this problem that I show you, we found that the electricity consumption in each neighborhood, the electricity consumption, the average, and the traffic on specific highways are more important. And from the weather, we found that the temperature and humidity and the wind are basically the main characters. And put them together, we come up with the causal model. And using this causal model, we'll be able to forecast electricity in next hour, next day, next week. And the same way, we can forecast the traffic in the future. So, we give you.
Can you help me understand something? So, what is the metric here? The 0246 to the 14. What is this value?
This is the percentage of the error for electricity forecasting. It's electricity forecasting as a minimum, as basically the average error for the forecasting. And
So
but I want, yeah.
No, go ahead.
So I want, no, I wanted to ask you, just look at this, the orange line. So
okay.
The orange line and the x-axis, the E means electricity. Basically, if we want to forecast electricity only by considering the historical value of the electricity consumption, that's the scenario 1, or just the only E. We got around maybe 12% error. You know, if we use the last month, in this case, I guess we use a three months data and we try to forecast the next day. So we got around, in that setting with that algorithms, the setup we had, we got around maybe 12% error. Then we also consider the weather. And because the electricity consumption is correlated, is dependent to the weather, having the knowledge about the weather basically give us advantage about understanding how the electricity consumption is. So combination of the electricity and weather, or EW, at the next scenario, help us to reduce the error to less than maybe 9%. An improvement.
Yep.
Then we did another step. Our hypothesis was the traffic in the same neighborhood has some patterns and correlation or dependency with the electricity consumption. So if we can combine the traffic data with the electricity consumption, we get better sense of the electricity consumption in future. Because the traffic has some information about our electricity consumption, back to the story I told you. And it seems our hypothesis was right. We could even improve the accuracy of forecasting even more than just considering the weather. So electricity and transportation made some improvement. And at the end, we put electricity, weather, and transportation all together, and we could even make a further improvement. But as you see in this orange line, there are this kind of saturation. So the improvement gets more flat and flat. There are some limitations. So, and this is something due to this information saturation. Basically, adding more and more data, more information sometimes may not make a big or a breakthrough improvement in our accuracy. So what we did, we started look at the blue line. The blue line is where we start to use our causal model. In other words, we start to cherry pick the useful piece of information, just something that has cause and effect relationship to the electricity consumption. And we've been more picky on just selecting piece of the data that really tell part of the story, which for us in this case is electricity consumption. So using the causality model and extracting the useful piece of weather data, we could maybe in electricity and weather, we could make weather improvement because we've been selected and we don't use the whole weather data we have with the all parameters or 20 something or 30 different weather parameters with the electricity. The same for the traffic. We didn't look at the whole traffic in the whole highways in the whole neighborhood. We just been picky and we be careful about which part of the traffic is more useful for us and is related to the electricity consumption in that specific target neighborhood, right?
So one more question that I mean, you've done an impeccable job on this graph, and it's very clear that you managed by combining weather, traffic, and electricity, and using the method, the causal based. It's very clear that the slope is down. The only thing that I still don't understand is the vertical axis. So this unit, what is this? Is this kilowatts? What is this unit?
So MAPE, to be honest, it's called the mean absolute percentage error.
Okay.
Mean absolute percentage error is a standard index for measuring the error, for the forecasting error. Basically, this is the error. This is the difference between what we forecast for the next day and how it is different with the actual consumption for the next day after we get the measurement. So it's the difference between the actual measurements and what we forecasted. And based on the, the mean.
I was a very bad student, Reza.
No. Even I forgot what was the P. It's percentage, yeah.
No, what I wanted to say is, as a student, I wouldn't let any faculty leave before I understand everything that they say. So,
yeah, that was regarding basically with that chart. I want to say that we need to be using the causality, the causal analysis, and combining the data from different infrastructure, weather, transportation, electricity together, give us these sharp trends in reducing the error or improve our forecasting. But there is another side of this story, kind of a big data dilemmas. We hear more and more a lot about the value, the magic of the machine learning and AI and the big data and how they change our life. And basically, they can be ultimate solution for everything, which is not true. In reality, sometimes having more and more data is just kind of having more and more noise, so it's not really useful. We need to be careful in terms of what type of data we are working and how we cherry pick and selects the best data, or in other words, how can we do feature engineering to get the best features which are related to our target variable. In this case, so we did 1 hour forecast, an hour ahead forecast, a day ahead forecast, and a week ahead. So 3 different horizons in future. And for doing this forecasting, we're looking at this 1 day before, 1 day history, 1 week, 1 month, 3 months, and 1 year historical data. And we look at the forecasting error, MAPE, and we try to understand how much historical data do we need to forecast a specific time in the future. So The blue line here is 1 hour ahead. So if for forecasting 1 hour ahead, we look at one day, a day before, we get around maybe 5% error. If we look at the whole week before, we reduce the error, maybe to some extent to 2 or 3%. But more than a week, a month, 3 months, 1 year really doesn't have a value. I don't need that much historical data just to forecast what will happen the next hour. So I can just pick what I need from the history. If I change it to the 1 day forecast, that I was talking about 1 hour. If we want to do it 1 day forecast next day, if I look at the previous day, the error is around 20%. It's too much. If I look at the 1 week before, the error comes to the 10%, and when it comes to the 1 month, it will be less than 10. And again, after 3 months, for the next day, really it doesn't help. So why we should keep all this data for that specific problem, and so on for the 1 week forecast. So basically, too much data also will be serve as a noise. That's another reason for using a method such as causality analysis, to be more picky and more careful about what data we pick to analyze.
So let me ask you this. Is this causality analysis, is it like, so in my domain in composites manufacturing, there is a lot of struggle that physics-based model won't get you there. And we talk about data-based models, and also data-based model are not going to get you there. I mean, it's a very complex manufacturing process to rely on data only. So what we're going towards is a hybrid physics data-based approach, where you have a physics-based model and a data-based model, and there's communication between them, and there is swapping to have better accuracy. Is this a little bit the same concept what you're presenting?
Absolutely, absolutely. I'm happy you mentioned to that, because we are also in the infrastructure dealing with that too much, and we would love to use the model-based approach, but the best model is no model, because when it comes to the modeling, it's about abstraction, to reduce the reality into the few variables that try to project the reality. So basically, model is kind of illusion of the fact of the reality, and that's what is there always. So we have some limitation mathematically to model precisely the physical phenomena, but model comes to the game at the very first days of the science, because it's made our life easier, right? So what we can do, as you said, and the reason we were so model driven in the past, and especially a few decades ago, was due to lack of the data, lack of sensor, lack of monitoring. If we could observe phenomena, we didn't need to model them, right? If we could put sensors everywhere, if we could put a sensor inside a combustion chamber, if we could put the sensors on a rocket and then we send it to the moon, and we could measure everything, we didn't need to have much model, because we could observe it.
Yes.
So I think with the advancement in the sensor network, in the material science, with building different type of the sensors, and with this connectivity and how we collect the data from the sensor, it's a time to put less weights on model. I don't say we should avoid model. No, always we need to have the model, because model is the way we understand the physics. But we don't need to be so worried about using very precise and high and very detailed models. So data help us, having some data help us to create higher fidelity models that can be used and explain the complex system. In terms of infrastructure, really sometimes the model doesn't work. There is a very famous quote for power system, and they say that the power system is an engineering system that doesn't work on the paper, but it does works in reality. So yeah.
That's a good one. I mean, you've raised a very important point, and the goal is not to make an accurate model. the goal is to make observation so that you can actually enhance performance, and the model is there to support that goal. It's not the other way around. And I totally agree with your assessment. So Reza, let's swap a little bit topics, and let's talk about co-resilience a little bit. So we talked about co-mobility and understanding how mobility actually influences certain patterns, and you can make sense of certain things, and we saw that on the power consumption and whatnot. So co-resilience, what are we? Are we starting a revolution? Resilience, what does co-resilience stands for?
Yeah. So first of all, the reason I am so in and sold out for resilience is really because of whenever we open the news, there are some kind of disaster somewhere, People are suffering because of the natural disaster, flood, earthquake, wildfire in California these days, I mean, hurricanes, what we see now in the basically the southeast, and I personally experienced multiple hurricanes while I lived in Florida, and really this kind of natural disasters impacts the life of millions and billions of people all around the world. So as an engineer, I think it's our role or mission is to do something for making life easier for people, especially when we are working on infrastructure. And that's the beauty of the resilience, to make the infrastructure somehow more flexible toward very harsh condition, in a way that it didn't break into the different parts, you just do not functioning, just have some level of functionality when it comes to the very harsh condition and natural disasters. So what is co-resilience? Very similar to the co-mobility. If we want to make a resilience network, resilience infrastructure network, we need to pay attention to the interdependency of that specific network with other sort of systems and networks which are adjacent and connected to that one. If I'm talking about the resiliency of the electric grid, we need to make sure that our roadways are resilient too, so we can have accessibility to the electric poles, transformers, substation, and facilities, so linemen and the utility crew can have access and go and fix those problems. If we are talking about this kind of the roadway and electricity resilience, we need to be careful about also and pay attention to the communication resiliency. We need to have connection between this first responder and the emergency management crew to go and fix the issues, so the connectivity is in line. And also the citizen need to be involved in this process. So co-resilience is about multi-network connected approach to create resiliency. And it means that in our specific research, we look into the impact of hurricanes in Florida. We look at Hurricane Irma, Hurricane Michael, and we saw how these basically emergency management responder react to such hurricanes, and how we can come up with a better planning for them. Yeah.
This is awesome. So, I mean, this is, and also this is very, very important. I'm looking at your awesome graphic as well. The relationship between demography, power outages, roadway closures, and the wind, and how. So basically, correct me if I'm saying it wrong. Basically, what you're saying is the goal is to create and to find dependencies and how things are connected between different viewpoints, so that when something changes in one of them, you are anticipating changes in the other, and therefore you can build a predictive model or an assessment or resilience of how they influence each other. Is that correct?
Exactly. And then also when it comes to the vulnerability, because resilience is a response to the vulnerability. If we have vulnerability, then our grids comes down and we experience outage. Due to the vulnerability, we will lose our roadways and we have roadway closure, or we will lose our telecommunication towers to cover these cellular networks for us. If due to this lack of planning and vulnerability, we will lose the facility, the capacity to in our hospitals to respond and to take care of the people who get injured during this kind of disasters. So, and that vulnerability is not just related to the electricity. It's also, as I mentioned, to the roadway, to the responder, to the firefighters, to the hospital. All of them need to work together.
So how do you connect? So I see the disruptions on the left. So power lines, road closures. So I mean, we're talking overall infrastructure, and then you see priorities on the other side. Is this like a model where it communicates, like it informs a hospital of something or law enforcement of something on its own? Can you explain a little bit more on that?
Yes, very good question. So one part of the equilibrium, part of the problem is that basically the technological infrastructure, roadways, electricity, water network, gas network, and so on, and how they are laid down on the grounds in the city, in the layout of the city. Basically, we need to know where they are located and where they are connected to each other. So therefore, when we are talking about the infrastructure, as the left-hand side picture says, it's better to look at this infrastructure as a multi-layer, multi-network entity and model the disruption and as a piece of this multi-networks aspect. But this infrastructure is serving people, is serving citizens, and everything is about the people who are using this infrastructure. We want to make sure that they are safe and they are in a healthy condition, or if they got injured or in insecurity, we bring them to the security and to the safe condition. So we look at the land use in the city. Are they residential, commercial, industrial, or they are the agricultural, or the kind of the green zone, or whatever? And based on the land use, we give different weight to the specific part of the city. Also, there are some important facility in the city, like hospitals, firefighter, police station, and so on, which are important when it comes to the disaster, to respond to the disaster and help people in recovery. So those kind of area are also very important. So when it comes to the disaster, we need to make sure that the critical infrastructure, important area like hospital, they always have the power and they always have accessibility. So the roads that ended to the hospital need to be cleaned so they brings the people quick to the hospitals, for example. Therefore, the weights the weights we give to each location is based on its land use and its functionality. And we put this on top of the infrastructure, on the roadway, wires, and pipes, and so on that we have in the city.
This is super clear and super important. I mean, this is when we say future factories and future, like in my domain in manufacturing, when we talk about the next manufacturing and the next cycles, I feel like what we're talking about is future city planning and future cities, how cities can be smarter, agile, functional, and resistant to disruption and so on. I think this touches on our lives, and this is very fundamental research. So I'm excited we're having this chat.
Thank you, thank you. So also, before getting to this, I want to say that in a term of history, our cities used to be more resilient because they were more organic, they shape naturally in centuries, and people get together and build those cities. So if you travel to some old cities today, in everywhere in the world, you don't see any straight road or any intersection, right? Because because all these cities built so organically, people start to build houses next to each other, and then bring the service together. They walk along the cities and so on. I think somehow we need to go back to the traditions, to the nature, to the organic cities, and that helps us to have more and more resilience. And this kind of organic cities, we have farms around the city, so they create even their food next to themselves.
It's very interesting what you're saying. I've been having this discussion with, and we've been talking that actually a lot of what we're doing is we're saying we have to go back to what we were doing, and like for example, the whole wave of organic food. All food was organic
Yeah,
before.
exactly.
I mean, it's just like we're going back to what we used to do before.
Yeah, I
So
think.
yeah, we are entering our last couple of minutes of the discussion. I mean, it always baffles me how quick these chats go because topics are interesting, and like I mean, I have personal interest, and so let's see. And the last couple of slides that you have, what are we talking about in here on this network framework?
So we look at the Hurricane Hermine, which happened in 2016, and during that hurricane, we've been out of power for a week, so it was very painful. So that was one of the motive. I spent more time on this research. But what we have here is the spread of the power outage at the left side and the spread of the roadway closure. And even visually, we can see how they are related and how they are connected. So another aspect of our research is to look at the spatial distribution of the outage using the GIS frameworks on all around the city, and try to find the dependency between the electricity outage and the roadway, considering the topology of the electric network and the topology of the roadway. Having this knowledge, this kind of models, we come up, we first of all, we considered, I a bit touched this in the previous slides, but we created a map for the loads priority, depends on their functionality. And then we look at the vulnerability of the city, depends on the shape of the area, the topography, the vegetation, how much trees are on the line on that area. Because if we have a line, high trees in summer, with the high winds, with the hurricane, the tree will be fallen and basically cut the wires and close the roads. And then we come up with a metric that called need for resilience. And that's a kind of a blueprint, a roadmap for municipalities, for electric companies, the roadway authorities, and basically we try to tell them where in the city needs more attention, needs more investment, and they need to do some kind of hardening and investment for it to be ready for the next hurricane. Basically, we learn from each hurricane for the next one to be more prepared.
I mean, this becomes like predictive maintenance, but on a larger scale for a network, for a
Yeah,
city.
for a city, we do predictive maintenance for a city, and also
I guess we're coming up to our last chart. So,
yeah.
so this is a probabilistic study.
Yes, basically it's a probabilistic study based on the outage we had in the previous hurricane and the vegetation and also the shape of the neighborhood, the city, and we try to forecast where, if we have a scenario for a hurricane with different type of the wind gust and wind speed, which part of the city will hit more and will need more attention. And that way, the electric company can basically depot the responder or the crane or whatever tools they need in a specific area, or basically that way they can come up with a better restoration planning. Yeah.
Awesome. And I guess there's a couple of acknowledgement. You wanted to
Yes.
thank a couple of people.
Exactly. I would like to thank my friend Ernest Goen in FSU, and also for very nice and talented former and current PhD students like Baran, Aybek, Alijan, Jose, Madvi, Michele, Mahyar, and Mustafa. Yeah.
So thank you so much, Reza. Let me switch back to this view. Thank you so much for the discussion and for opening our site to the importance of how these topics can help us not only plan, understand, and make our today's lives better, but also aim for, the future to be more organic and the growth to be more going back to the roots. Let's put it this way. Is there any final words you want to say, Reza?
I want to say that everywhere in the world they have their own tradition, their own way of living, and they use the local material for building houses, for design the roads and everything. So it's very important to adopt and to build something which is specific for that area, considering the climate, the weather, and even the culture of that people. When it comes to the design of the electricity network, roadway, and cities, and being organic also means to pay more attention to the local aspects of urban design and infrastructure design. Yeah.
Thank you so much, Reza. It was awesome having you. I'd like to ask from everyone on the chat to throw in a thank you, one of these clap buttons or so on, just to thank you for your time. And we stay in touch. Thank you, Reza.
Thank you so much. Thank you.
So let's wrap it up. I want to throw in a couple of comments, and before we close the discussion, first of all, Yunan, thank you so much for the very, very kind comment. Hi back to you and to your brother Sherbel. And Mazen, I wanted to say all the love back to you since the course at the Lebanese American University. All the best for you. My students are everything for me, and this comment is very, very dear to my heart. Thank you so much, Mazen. Thank you, everyone, and mostly thank you to Reza for this wonderful chat today. Talk to you next week.